Today we're going to look at properties of logarithms, and a logarithm is really just an ugly way to say an exponent. If you have something in exponential form, like a raised to the b equal to c, you can rewrite that using its logarithmic form. Log base a of c is equal to b. Through this rewrite, through the shifting of the variables, what you're really finding is the inverse of the exponential function. So if my exponential function is f of x, and I work through the process of finding my inverse, it's going to look like a log base a, where a, this base, will match the a from this base. Everybody will just kind of be shifted around. We're going to use that idea that these two are inverses to help us solve logarithmic equations. Specifically, we'll be using these first two rules, where if I have log base a of m equaling something, I can raise both sides up to the a and undo the logarithm. So if I had something that looked like log base 2 of x is equal to 9, I can raise both sides up to the 2, and 2 raised to a log base 2, if the bases match, will undo itself and be left with a 1. And so now all I'll have is x equal to 2 to the 9th, which I can plug into my calculator. If I have an exponential and I want to go over to the log, if I want to pull down the exponent, I can take the log with the base that matches the original base from my exponential. So I could say log base 10 of both sides. Log base 10 of a 10 is a 1, because 10 raised to 1 power will give you out of 10 a 1. And so you're just left with the x equal to a log base 10 of 7. And when it's a base 10, you don't have to write the 10. We call that a common log. Conveniently, we have a common log button on our calculator. So if I wanted to find out what log of 7 was, I can just go into my calculator and type it in. Now this calculator button is only for a common log, for a log base 10, and you can see above it is its inverse, right? 10 to the x, just like x squared and the square root of x are inverses. If you want to find the log of a base that is not a 10, we're going to have to use another rule, and we'll look at that later on. Right now what we're going to do is practice using some of the log properties to expand, but more likely later on you'll use them to condense so that you can use one of these two rules up here. Although the expressions will look very complicated, there's really only 3 rules. There's the product as a sum rule. So if I have 2 numbers being multiplied inside a logarithm, I can separate them using addition. We get this rule since we're working with exponents when we're multiplying bases that are the same. So when I had x squared times x to the 3rd, I added those bases together for x to the 5th. And so since a logarithm is just an ugly way to say an exponent, that's where that rule comes from. If I have 2 numbers being divided, like log base a of m divided by n, we'll split them by using log base a of m minus log base a of n. Again, this comes from your exponent rules. If you had x to the 5th over x squared, you would subtract those 2 exponents and be left with the 3rd. The last is from the power to a power rule. So if I had x squared to the 3rd, you would multiply those 2 together. And so he would be x to the 6th. It will look a little different when we're looking at the logarithms, but you really, when you have a logarithm raised to a power, it's a exponent times an exponent. That's why we can just kind of bring it down out front and multiply the 2 together. So let's look at all 3 of these rules in one. I have log of a 4x squared over a 75y squared. I'm going to work with common logs just to keep it a little bit neater, but if this was a log base 2 or a log base 7, you would do the exact same thing. I'm going to start with separating these first because it would look something like this, and I'm going to work with this big division problem first. So I have log, now base 4x of 2 minus log base 10, and I don't need to write the 10, of a 75y squared. So now that they're split into 2, I can work with each one of these individually. Inside of each of them, I have an m times an n, right? M times n, m times n, and I'll split those using addition. So I have log of a 4 plus log of x squared minus, I will use parentheses, log of 75 plus log of y squared. The last thing that you're going to do when you're expanding is deal with your power to a power rule. So anytime you have a log raised to a power, like we have right here and right here, that exponent that's on the variable will just come out front of the logarithm as a coefficient. So I'll have log 4 plus 2 log x minus, parentheses, log 75 plus 2 log of y. They will not look neater when you're done. They're going to seem a lot longer, but sometimes it's easier to deal with one simple log than one very complex log. More than likely, though, if you're working with logarithm properties, you're going to want to condense multiple logs back into one log. And so instead of working like we did from the single log down to the many, you're probably going to want to go from the many all the way back up because we're going to be solving equations. And so as you would suspect, you're going to be using the same three properties just in the reverse order. So if I had 1/2 times the quantity log x plus 2y minus a 3 log 6z, I'm going to go through the process of condensing this together. I'm going to start with parentheses. You almost always want to start with the parentheses. And then you're going to go to your power to a power rule. So even though we did power to a power rule last before, when you're condensing them together, you're probably going to want to start with that. Of course, the one caveat is that you need to deal with parentheses first, always because of PEMDAS, right? Parentheses, exponents, then multiplication and division, then addition and subtraction. So I'm going to have this log x plus a log 2y. I'm going to squeeze them into one log for a log 2xy. And I have a log something that looks like that. Minus 3 log 6z. Now I'll deal with my power to a power rule. This 1/2 is going to come up. Now when you're pulling a exponent up and you have multiple pieces inside of the log, so there's more than one variable in your term. Like I have an x and a y. Over here I have a 6 and a z. The 1/2 or the exponent that we pull up, like over here it will be a 3, needs to go on all 3 pieces or both pieces on the inside. So it goes on the whole piece that's inside the logarithm. So it's not going to just be on the y, it's going to be on the 2xy. And so I'll have log 2xy all raised to the 1/2. And then when I pull up the 3, regardless of what your sign is out front, you always pull up the absolute value of the number, right? So I won't pull up a -3. I'm just going to pull up a 3. And that just doesn't go on the z, it goes on the 6z. So I have 6z cubed. At this point, I can either rewrite my exponents and kind of use my power to a power rule for exponents, or I can leave that to the end and do my division first. I think I'll do my division first. So if I have it separated with subtraction, I can put these back together using division. And so I have 2xy, all of that raised to the 1/2, all over 6z raised to the 3rd. And that's as condensed as it's going to be, so it's only one logarithm. But you may want to rewrite your exponents. When you have rational exponents, remember, that really means that you're dealing with a radical. And so that would look like the square root of 2xy. And 6z times 6z times 6z is going to be a 6 cubed times a z cubed. And 6 cubed is 216. And so I can say log square root of 2xy over 216z cubed. And that's going to be the most simplified form. Once it gets to that form, in the event that you had this equal to 5 or a number or any other, maybe another variable, you would then want to use those two rules that we saw before. In this case, we would kick this up both sides from the 10. Sometimes you have the 10 and it works out nicely, and then we could just use our common log button and we're all done. But sometimes we have to use one more rule, and that's our change of base formula. Change of base formula, usually when you first see it, we talk about logs with different bases, but you can also choose this base sometimes. And so you don't necessarily always need to match a base. You could use what we'll later see to be a natural log of both sides, although we haven't worked with many natural logs yet. So for now, I'm going to stay with this top one. So for example, if I wanted to solve this exponential equation, it's one that is unlike the ones earlier in the chapter, right? Because I can't write 7 as 2 raised to the something. If it were an 8, that would be easy because 8 is 2 cubed. And now my bases match, and I can do my work up in the exponents. I can't do that with a 7. So I'm going to need to use a logarithm to undo this exponential, to go from one form to another. And so I'll take the log base 2 of both sides. Log base 2 of 2 is a 1, and so I'm left with just the x. Of course, it's a power to a power, so my x comes down out front. And then this side is now a log base 2 of 7, which I don't have any way to deal with in my calculator. I don't have a log base 2 button. I only got a log base 10. And so what change of base says, well, you can pick your base, any base you want, so I'm going to choose 10 since that's what my calculator has. And I'll say log base 10 of x, which is the 7 in this part of the problem, over log base 10 of my b, which is a 2. And now I can plug that in my calculator. I can say log base 7 divided by a log base 2. And you'll get a crazy number, and that's okay, 2.81-ish. But 2.81-ish is what 2 raised to this number would give me a 7. So if I said 2 raised to the answer that I just had here, so I'll say second negative sign. So 2 raised to 2.80734 ... you'll get a 7. And so for change of base, it's very forgiving. You can use any base that you want. So why not use a 10? Later on, when you get more comfortable with E and natural logs, you can use an ln.